And before joining the computer vision and whatever, I did a PhD next doors in UAB. And I did a PhD I finished a PhD thanks to Giulio, who is maybe my biggest hero in the world. He saved me and everything. And we work with quantum sensing, which is a fantastic topic. And Giulio is a reference worldwide on quantum sensing. So maybe I know his curricula by heart, but so Giulio did his PhD in Trieste, right? Working on something a bit more like theoretical physics. This I forgot, maybe. Well, this I totally forgot, but then he moved to, well, on what did he do the PhD?
So if you want, I can introduce myself. So,
well, it's less boring, okay.
Okay, so yes, so I did a PhD in Trieste, where I worked on foundation of quantum mechanics and over quantum system dynamics. I explored a bit collapse models, interaction between quantum mechanics and gravity, and collisional models of quantum systems. Then I moved to Southampton in an experimental group, because actually I was curious about better understanding measurements in a lab. And there I continued to work in foundations mainly, but on the experimental side. I didn't do any experiment. I only had them with a theory, developing the theory of these experiments. And there we basically study experiment to test quantum mechanics and gravity per se. And after that, I moved to Barcelona, where I met Mattia. And there, together we work on mainly quantum sensing. And now I'm in Siegen, where let's start to say what I'm doing here, because there are several things together. And I'm working on dynamics right now, quantum system dynamics. Still interested in estimation and quantum sensing per se. And now I also restarted to think about foundational quantum mechanics and interaction between quantum mechanics and gravity. And basically that's it.
Okay, cool. And this seminar is actually super important because for the scope of engineering institutions like CVC, it's very hard to know there is more than quantum computing and this NISQ variational quantum algorithms out there. And indeed, there is way more. So recently, Giulio, in collaboration with JIG, put out a paper on quantum sensing and a problem that can easily be complemented by machine learning. So I guess it's likely Giulio will talk about that and more. So well, people say the floor is yours. I'm not very sure if it's right or not. But Giulio, whenever you want to begin, you can share your screen and I will stop sharing.
Yes, sure.
And thanks again a lot to give us the seminar.
And for you to inviting me here. So 1 second. So now you should see my screen. I don't know if you can still. Is it?
Yes, very good.
Okay.
And one question more. Do you mind if we interrupt you and ask questions? And
No. It's totally fine. It's actually better if you interrupt because I didn't know which was exactly a target. And I guess for some of you will be a bit boring because there is a very general introduction on quantum sensors per se, and which is done for people that know nothing about them. So if you are a quantum physicist, maybe you will find it boring. And then the goal is basically to show you how we can extract information from these devices. And in this, I would basically talk about how it's done more or less in the standard way now and what we can do better. And later on, I will move to show you how to use machine learning tools to learn both device parameters from these quantum sensors and external sources. So let's start for what is a quantum sensor. And a quantum sensor can be this nice device that we have here, which is basically a gas vapor chamber, and or this other object here, which is basically a membrane that can be put in a quantum state, and then some readout, without some information about this object, or this other object here. But what they are, at the end of the day, they're not just a quantum system, which evolved by some dynamics, which is this object here. Usually here I put it L because I'm imagining that it's not just a standard Hamiltonian dynamics. It could interact with an environment, and then dynamics is a bit different. But don't worry about it. This object can be understood just as the evolution of the system. You start from a system time t, and you move to t plus delta t via this expression here. But it's not only a quantum system, it's something more. It's a system which is monitored. Meaning that at each time step, we extract some information from the system. And as you may or may not know, when you measure a quantum system, there is a back action on it, different from what happened in classical mechanics. And this can be a problem. Indeed, what can happen is that if we have too frequent and too strong measurements, they will freeze the evolution. So the back action will be so strong that will dominate the dynamics and will basically freeze the system in the state in which it is. This is a problem if you want a sensor, because you would like to this system to change in time and extract information from it. And the way in which is basically this problem is overcome is using weak measurements. So measurements that are very low informative, like as you can see here, for example, is a weak measurement in the sense that what we want, we would like to extract information about dy, that is basically some information about the system, and what we get from the measurement is the dy. And as you can see, there is a very large uncertainty that is proportional to power delta t. And that is small, basically, actually, here there is a mistake. This delta t must be the top. Delta t is small, the variance is very large, meaning that the information that we gain is not actually informative, is very low informative, because it's dominated by noise. Indeed, if we have weak measurement, we pay having our signal, which is very noisy, as you can see from this, which is a simulated signal from a monitor system. But what we gain is that now the system is influenced by the measurement, which will be this added term from the free dynamics, but in such a way that we can still extract information from it. So it still retains its dynamics. And here I show you basically the standard prototype of this measurement, in which we have this part here, which is basically the quantity that we measure from our system, and this term here, dw, that I call innovation, which is nothing more than the signal that we get from our measurement minus what we extract. And if everything is done correctly, this one would be, if you know the term, a peanut noise. Now, since this is but actually, it is not only, but a sensor needs to send something. So what we need to add an input, which is a signal. And then once we have our monitor system, we let it interact with something else, which is this input. And then we have our sensor, basically a system in which now the dynamics is influenced by this parameter theta, which is basically describing the effects of our input. And the equation doesn't change from the side of the measurement, but now the dynamics, as you can see here, every time that it's influenced by the action of our external source. And it's basically what a sensor, quantum sensor is. It's not different from a classical sensor. The only difference is that, I mean, practically speaking, the only difference is that our system is quantum. It behaves quantum mechanically. And for this reason, every time that we measure the system, we have a back action on it. But okay, and of course, but okay, since the questions that I showed to you are a bit too abstract and complicated, and actually most of the system that we use, they work in a specific regime, which is a linearized regime of the equation that we have. In that case, what we can do, we can actually simplify the equations and describe the state of the system just via its spin, the quantum system by spin, and its variance. And the equation simplifies as you can see here. I show this equation because basically it's how we mainly treat our quantum sensors. But also for
do you mind, Julian?
Yeah.
Do you mind if I jump in? I'm super sorry.
Sure.
But thinking on someone that will hear this talk in about I don't know, whatever, one day or whatever, coming from machine learning, maybe it would be super nice to clarify that the equations, like the Palladian or even more like the stochastic quantum equations, no, this one, are essentially impossible to solve, no? So,
analytically, you mean?
Yes, exactly.
Okay, yes, okay, that's true. I mean, there are very few cases in which we can solve the equations without this part analytically, and when we have basically the feedback due to the measurement actually become almost impossible, especially because our dynamics, it depends explicitly from our measurement device. But maybe what is useful is to see what happened in this Gaussian regime. Because maybe if you come from machine learning or sensing in general, maybe you can recognize this equation. Because in this case, they reduce to what are called Kalman filter equation. And if you are not familiar with Kalman filter equation, an equation that are used to were invented by Kalman and was a technique to basically estimate the position of a system, the optimal to estimate the position of a system which undergoes under a non-dynamics and a noise. And by chance, let's say, if it's not, there is a reason for why the dynamics of a quantum system, in the case in which we reduce the Gaussian regime, is exactly these equations, which are as maybe Matthias said, is basically they are to solve. And what we do with this Kalman filter equation, we basically solve them numerically in general. But okay, now that we know what a quantum sensor is, maybe we are interested in extracting information from this sensor. And actually, what is done in general is, for example, extracting parameters from this sensor, from the dynamics of this sensor. And what is usually done, we have our nice time trace, which is basically the sequence of outcomes that we obtain from our from measuring our weekly monitoring our quantum system, and then we don't use directly them. We we combine them and we build correlations or even the average, and then correlations between these outcomes. And then we take an average. It is a stochastic average, meaning that we repeat the system, the experiment many times, or since if we are in a stationary regime, what we do, we basically chunk this signal time tracing blocks and use these blocks as a new experiment and use them to build the average. We do a Fourier transform of this object, and we obtain what is called the power spectral density of our system. And from the other side, we have our theoretical model, which is basically this one. We compute the correlations of our system. We do the Fourier transform, which we know how to do analytically in this case, and we obtain our theoretical power spectral density of the system. Now, what people have proven is that this power spectral density is proportional to this one. And then, basically, what is done, it's just a fit of the spectral density obtained by our data to the spectral density obtained by our theoretical model. And it works pretty well, actually. Indeed, at the point pretty well to estimate parameters of the system and to extract some information about the system. But to obtain this match, we need to assume Gaussianity of the system. So this is certain questions, because for this one we are able to obtain this object, and stationarity. So meaning that our system has been a stationary regime and is not in this transient moment in which it's still evolving somehow. This is very nice. Indeed, the strategy is actually optimal to estimating parameter of the system. And with asymptotically, I mean, if you have a very long time trace. This asymptotic means that the length of the time trace is to infinity, and we can prove that it is optimal in this case. It is used and understand, as you have seen. But actually, okay, this is more a con than a pro, because this should have been in cons. But there are a lot of cons, because it works only in the stationary regime. That does not use all the information in the time trace, because we only use a transform quantity, a filter quantity, which are these basically correlations. And it does not work in real time. And furthermore, needs a model for both the sensor and the force, a specific model. And if the force is varying too fast, in the sense that it's varying with the same scale in which the quantum system is varying, it cannot be applied. Because if this force is varying too fast, the system will never be at equilibrium, and will never have the stationary regime condition. So the question is, if we can do more. And actually, we can do more. And for that, we can use Bayesian learning. I don't know if you are familiar with that, but the idea is that we have a set of space state, basically, that describes all the hypotheses we have, a set of data, our evidence that we have it, basically our time trace. We need a prior belief, a conditional probability that is given by this probability that we have in our measurements, and then from them combined together we obtain our posterior here, which is not our prior belief time, our conditional probability is divided by the probability, this optimization factor here. And with this, what we get the probability of having one of the hypotheses given our set of outcomes. But how can we use this on our system? Basically, we have our output. Now, what we do, we can take our output. We have our theoretical model, which we know it is described. We feed our output in our theoretical model, one output at a time, and then we obtain our estimated output from our theoretical model, and then from the weak measurement model that we had before, we obtain our update rule. With this update rule, we obtain our probability of the outcome of the full time trace. It's pretty easy because they are this probability IAD, and from that we apply our prior, and with the prior we obtain our posterior. Now that we have our posterior, we would like to decide which is the best parameter describing our model. And one way to do it is just to maximize the probability. And if you maximize this posterior probability here, it's like minimizing the log of this object here, of this object here, over theta, because this normalization factor here doesn't play a role in the maximization. But actually, using just pure Bayesian learning is fine and will give us a nice result, and will work, as you can see, can also work in principle with fast varying signals, and doesn't require the system to be in a stationary regime. But and actually, it's still but it's computationally expensive in the sense that computing P is very difficult to handle, and still needs a model space to operate, a specific model space that must be defined in advance. Pretty clear one. So, but I think, but it's hard to handle. And I think there's also this other idea that conceptually wise is a bit harder to understand. Okay. Now that I just introduced this Bayesian learning, let's see how actually, instead of using using all this machinery, all this machinery here of this Bayesian learning, we can see it as a machine learning in a machine learning perspective. What we can do actually, we can think about replacing all the machinery with a recurrent neural network. So as you can see here, our model is very similar to what you expect from a recurrent neural network. So you have you feed your system with the data. You have your update rule given by your model. You actually and your model actually give to you a synthetic data to compare. And meaning that we have all the ingredients. And actually, if we build this neural network, what we can do, we can build that now. We can minimize a cost function, which should be let's say the mean square error plus some regularization factor that we had here, as standard is customary in this typical problem. And then once we have the data, we feed them in this neural network, and then we minimize we minimize our cost, we feed them back, and we continue iterating until we get a nice outcome. And it's much simpler than basically to understand the machinery that we used before in the Bayesian sense. But of course, now the question is how we build this neural network here. And let's start with just a monitor system. No signal acting on it. What we have our model. Here we are just in the Gaussian regime, but it's totally fine. We have our dynamical model for our system. And now the update function that we had before is replaced by this object, which is basically the state expression for the update function. And now our recurrent network is basically as this structure here, which is the update dynamics of our system, which is fed by the data that we get from our system, and then basically our estimated signal. And with that, we can basically estimate any our system. In this case, I'm envisioning an optomechanical system that has a specific oscillation frequency omega, a damping rate gamma, and some other terms which are kind of irrelevant for the discussion. With that, actually, we have the structure of our neural net, which is physics-driven. Everything is model-based. And with that, actually, what we can do, we can estimate parameters, for example, the frequency. And if we run our neural network with this recurrent cell that we said before, and we minimize over the mean square error. In this case, since on the frequency there is no regularization needed, what we see is that actually our neural network works pretty well, and actually after only 68 iterations, it almost matches the true value of our underlying model. And if you look at this plot here we compare basically the blue line is the best achievable the error from any test, and with the light green we have our machine learning error, and with the dark green the error obtained. And as you can see, they're very comparable, and it seems here that actually the machine learning one beats the the standard power spectral density fitting. I mean, this is not, I mean, I believe that the fact that here is actually beating the standard fitting is just a numerical issue, because in principle, they should give more or less the same result asymptotic. Because we can prove, at least for this simple case, that both of them are asymptotically optimal. But okay, this is just to show you that this method actually works. But what if we want to include an input? Now we include an input, which is this bit E here, and we don't have a model for our signal. We don't have it at all. And here, actually, what we can actually use something that was done in the past, and it was this idea that came together with Matthias to use Cindy, which is this technique, this data-driven machine learning technique developed by Barton and collaborators, I think 2017 or 18, I guess, the first paper, which basically try to learn from the data the dynamics of a system. And the idea here, at least in Cindy, is pretty simple. Here, I mean, this panel here is taken from their paper. And what they wanted to do here, they wanted to reconstruct the dynamics of a Lorentz system, which is about these equations here. What they did, they defined their network as basically these objects here, which are these objects are just matrices containing a full dictionary of functions, and then our parameter xi to be determined. And then they added some sparsity on this on the minimization cost. Doing that, actually, they were able to they shown that they were able to recover the Lorentz dynamics, or to learn the Lorentz dynamics without noise. But what we did, we basically take the same idea. Indeed, we model our signal as a differential equation. We define basically our dictionary of functions, which are can be anything, can be a set of, if you think about, I don't know, can be polynomial functions are here, or trigonometric functions, or anything you can envision. And they can be tuned to better match the characteristics of the system and to speed up basically the conversion of the model. And then there is this set of parameters here that just select a weight on this set of functions. And then in this case, since we don't want to populate too many, to have too complicated dynamics, and we believe that physics is simple, we apply basically, we impose some sparsity condition. And we end up with basically a lasso approach, which is this one. And basically that's it. Now, in this case, we have our, even if we have an input system, we can actually have our recurrent neural network, which is described, of course, contains all the information about the model of our sensor, plus our unknown force that must be discovered. We want to discover the dynamics. And now to test it, actually, what we did, we applied this scheme to this, assuming that the signal to our system was this FitzHugh Nagumo model, which is a model for neural activity. Why choosing this one? I mean, it's driven by two ideas. One is because most of the sensors now, some of the sensors now, they're used to actually measure, they are trying to use them to measure magnetic field, and I try to use them actually to measure the neural activity. Another one is because this is a non-trivial model, as you can see, that can have also some instability embedded in it.
And sorry, Maybe one motivation more is that you can actually use this quantum sensing platform to measure neural activity in principle.
Yes, thanks. And of course, now we have our recurrent neural network. And what we need to define is our function dictionary. And what we chose polynomial functions, meaning that basically our signal model, so our function dictionary, is of this form. As you can see, we have our two signal B1 and B2. We have a constant term, a term of parameters that selects the linear form, and then a quadratic form, and then this matter, and so on and so forth. In this simple example, we stopped to the cubic term because it was just an explorative test. And we assume these parameters here. I mean, this is basically this part, the second part, and the last 3x3 array gives you this array here that are fitted in actually the model that we used. And with this model, I just showed to you the signal that we get for B1, which is this basically this shape here. And then what we did using this scheme, we just train our neural network, and we end up with, okay, this was the network before any training, and this is what we got after training the network. Here, I show you basically the two signals, the two, let's say, hidden state of our sensor, which we have access of because we are simulating it, and the one learned by our neural network. They fit pretty well, except from some small points. And the same for the signal. As you can see, what we see is that actually the signal that we get from our simulated signal and the signal obtained from our neural network is similar, but the one from our neural network is it's less noisy, which as it should be actually. And sorry for the image. I don't know why it's so low resolution. And here are the results actually of the network. And as you can see, the numbers fits pretty well without any without optimizing too much on the network per se. This is also to you the idea that this neural network can be used. But just to give you, to summarize more or less what we did and how all this machinery works is the following. If you want to rephrase it in this neural network formalism, we have our hidden process, which is our true quantum sense that is influenced by the measurements and measurements here. We don't have access to this part here. What we do in this scheme, we feed this one to our neural network, which is this object here. And the neural network just without some estimated signal. And then what is done is basically a minimization cost function is defined, minimized, repeat the interaction many times until we get the convergence. And the neural network in this case was this step here. Of course, one can think about a more general structure for the sensor, or even be something that first a neural network that first learn dynamics of the sensor without a signal, and then add a signal later on. But maybe something that we can learn from all of this, it's also that Bayesian learning can be understood under machine learning perspective. Indeed, I showed you that basically what we needed is a state space, data set, and the is posterior. Actually, to estimate the best parameter, what we do, we find the maximum of this, the value of theta that maximize this posterior probability. And now, if we saw this correspond to the R mean of the log of this quantity here, which in the case of the machine learning scheme is basically this part, which is the mean square error, plus our regularizer. Now, the interesting part is that this regularizer added in this machine learning scheme can actually be understood as a prior in our Bayesian update rule. And the prior that achieved this regularization actually, which is basically telling us, so this regularizer in this case can be actually understood as our belief, our prior belief on the data, on the structure at least of our data, to be sparse. So no many terms of our matrices describing theta, they count in our model. So we believe that somehow there is this sparsity, implicit sparsity in our model. This is, for me, it's nice because it connects somehow the pure machine learning perspective starting from a minimization cost Bayesian learning. Okay, apart from that, let's summarize and basically conclude. I think that what this shows is that basically continuously monitored quantum sensors are naturally state-space model. It's quantum physics, quantum filter, so basically the dynamics, and the physics can be described by recurrent neural network, which can give us can allow us to extract the likelihood, or basically the possible probabilities. And treating our continuously monitored quantum system, actually, this sensor as neural network allows us actually to estimate parameter near Fisher limits, and in some cases perform standard methods, but also to perform single-cell models recover hidden forces from indirect measurements, and maybe something more that should get explored. I mean, just as a take-home message, we actually don't need machine learning to write down quantum sensor models. We already know how to do it, and we are good on that, but we need them to fully exploit the real sensor, exploit the data that we get from the sensor, and extract information from them. And maybe to build richer inference tasks. With that, I conclude, and I thank you all for your attention. If you have any questions, feel free to ask.
Cool, thank you very much, Julia. Amazing. So, I have many questions that I always had in the past, but maybe to break the ice, and if someone has questions, please. Actually, we will organize one seminar more, at least, which is happening next week, and well, she was a postdoc from Mario Kren's group, and all this, and now is starting a new group in Germany. And so there is all this line of for discovering with machine learning architectures to do better quantum sensors. Do you think that in continuously monitored systems we can actually to optimize? Do you understand my question, like how to construct the quantum sensor?
So in principle, if what you can do, you can invert the problem here and assume that you exactly know the signal or the characteristics of your signal that you inject on your system, and you have a big understanding of your sensor, in a sense that maybe you have some structures here, maybe not. And then you can try to find the optimal parameters of the sensor such that maximize the outputs from the signal that you inject. And in that case, you are learning these parameters here more than learning the signal. It's basically, I mean, it will most probably work out, even for this to optimize the parameters of your sensor. And even if you would like to add more features, like, I don't know, you want to go to non-Gaussian sensors with specific structures, you can embed some structure in your physics-driven model, and then let your neural network learn the parameters.
Okay, and maybe one more question to motivate for the people that eventually will listen this and that do not have a quantum background at all. Which the of this in the say, I don't know, industry or
you mean quantum sensors?
Yes.
Okay, so there are, it's hard to tell, but there are these gas vapor chambers that are used to measure magnetic fields, and even squid, which are used to measure magnetic fields, already out there. Squid are mainly used in the scientific sector, so as sensors for experiments more than in real life application, because they need to be at cryogenic temperature, which is hard to achieve. I know that there was one experiment done with DC used to measure the Earth gravitational field. So they built this piece, they put it on a boat, and they were traveling around and measuring basically the variation of this piece. And it's something, but the problem in that case is that the system is very unstable. But there is a great interest in, so since these systems are very sensitive to any perturbation, there is a great interest to use them to, for example, to measure variation of the gravitational field. And the main reason is basically money in the case, because people want to search for, the company wants to search for oil. They don't want to waste time or resources drilling just around randomly. And if they have a better precise sensor, they can save a lot of money. On the other side, there are these ultra precise clock that, if you want, they can be understood as sort of quantum sensors. And they actually are very sensitive to variation of the gravitational field as well. But I mean, there is nothing ready to market right now, I would say. And people are starting to explore basically all these this kind of devices.
Cool. Fernando has the question. Thank you very much, Julian.
Yes, Julia, thank you very much for the very nice presentation. And I have a question regarding the functions dictionary, more curiosity. Are there any specific conditions that the functions dictionary can have, or limitations in order to be used? So this is something that an area of potential research, and how to implement these functions, or how to, in some way, decide other type of dictionary.
I mean, I think, in principle, you can expand a function in polynomial as an infinite series of polynomials, but I need to truncate. And then the truncation will add an error. But, and this is a limitation if you want, but I think the dictionary must be chosen thinking about more or less the kind of signals you would like to detect. And if you already know that the signals will have some periodicity for some reason, then maybe it's better to use trigonometric functions. And this most probably will speed up the convergence of your algorithm. And so it's
this was my as a matter of fact what I was thinking, to some way the potential probabilistic for speed of convergence would depend on the actual set of functions that of the nature of the functions that you pick from the dictionary.
Yes, of course. Yes, it will. This is something which I mean, I don't know. I wouldn't know how to select the dictionary agnostically, let's say. So you can start with a good guess, let's say. So in the sense that if you start with a polynomial, it's not bad. You will extract some features. But then if you discover that the signal is like oscillating, maybe it's better to switch to some other dictionary. So it's something that what one could do maybe is just to use part of the signal that you get to select the dictionary if you want to have a better neural network. So you have a set of dictionaries, and then you extract some rough features of your signal, and from that you select the best dictionary for your scope. That could be an option, but we didn't explore that, to be fair.
Good. Thank you, Judith.
Sorry.
Well, I remember there is sort of a motivated basis for these functions, which are called Walsh functions, but we didn't explore this at all. But on the other hand, I believe that there is a role in the autoencoder that can play on finding the right change of basis somehow in this in the approach. Maybe one room that I mean there is a lot of room to add on this idea, and what we haven't explored, and it could be super interesting for the scope of the computer vision center, is how you plug all the attention mechanism and all the transformer machinery to this setting, because we are here just using like the most basic recurrent neural network cell that you would think on. This is something that that could be, well, a game changer maybe. So nothing. I wanted to add that.